Okay, I think let's start then. Okay, let's start. Okay, so good afternoon, everyone. Okay, so we are going to actually learn about transition elements. Yeah, this is going to be part one, part of it. Yeah, so we are not going to cover everything today. Okay, but if let's actually start. Okay, let's start. Okay, about transition elements. Okay, what are transition element? Yeah, according to the definition, because according to our syllabus, you need to define transition element. So according to the definition, this one taken from your textbook, is going to be a D block element, okay, that forms one or more stable ions with incomplete D subshell. Yeah. So you must actually make sure, okay, the transition element, okay, these are going to be, if you look at your periodic table, okay, we are going to separate this into blocks. Yeah. So these two, okay, group one, group two, we call it S block. Yeah. And then from here all the way to here, we call it D block. Okay, and from here onwards, we are going to call it as P block. Yeah, the reason why we have separated them, okay, accordingly, because the last electron, okay, the outermost electron, or we call the valence electron, they are going to end at that particular orbital. Yeah, like for example, if I want to write down the electronic configuration of magnesium, okay, in simple form. Yeah, I'm not going to actually waste time over here. In simple form, it's supposed to be the neon. Yeah, the neon. Then I put over here, this is going to be 1, 2, 3. So it's supposed to be 3s 1, 2, 3s2. Okay, that is going to be the way to write. Yeah, so if you are confused on how to use this method of writing, yeah, or let's say for example I want to write down for scandium. Okay, how do I write this? Okay, this one I think please refer to your teacher, or maybe I'll make another video, okay, on how to write in simpler way, okay, when we are using the periodic table. Okay, so if let's say for example I want to write down for scandium, okay, scandium is going to be, okay, you can see here, this is going to be 4. Okay, the group 18B4 is argon, so I will write down argon to the bracket. This is 4, so 4s2, 4s1, 4s2, 4s2. Then starting from here, you must start from 3d. Okay, not 4 anymore. So 3d1. Okay, this is how we write for scandium. Okay, so the idea over here is, okay, if I erase this part, the idea over here is, okay, this part, okay, from here to here, they are known as your D block. Okay, D block. But under D block, not all of them are going to be considered as transition metal. You can actually see scandium, they are not transition metal. Okay, zinc, they are not transition metal. Okay, why? Okay, I will just show you very quickly why they are not transition metal. Okay, because when you write down the electronic configuration for scandium, it's supposed to be argon, okay, and then you have 4s2 and then 3d1. Okay, scandium will always form 3 plus. Okay, that is going to be the common ion, okay, that is formed by scandium. When you remove the electron, okay, please remember this. Yeah, when you remove the electron, we always remove from 4s first. Okay, remove from 4s. When we put in also, we put in 4s. Then after that, we put in 3D. Yeah, because the energy level of 4s and 3D, they are almost similar. Yeah, so when you remove, you also remove from 4s. So you need to remove 3 electrons. You remove 1, you remove 2, so it will become 4s0, and then you remove another one, it will become 3d0. So I will write it down as argon, okay, 4s0, 3d0. Okay, now if you look at the ion do not have any electrons in the 3D subshell. According to the definition, you must have, okay, one or more stable ion with incomplete D subshell. Yeah, incomplete. Okay, so it means that at least must have something lah. Yeah, in this case, the 3D shell subshell is not being occupied at all, so they are not going to be considered as transition metal. Okay, for another zinc, yeah, zinc is not also considered as transition element. Okay, because zinc, okay, if I write down for zinc, it's supposed to be argon, okay, argon, and then 4s2, and then this is 3d10. Okay, now if I remove, okay, zinc always forms zinc 2 plus. So when I remove the two electron must be removed, okay, from the 4s, okay, not from 3d. Yeah, the 2 electron must be removed from 4s. You are going to get argon, and then you get 4s0 3d10. And in this case, you can see the 3d subshell, yeah, the orbitals, okay, they are going to be complete. Okay, we want them to be incomplete. So therefore, zinc is not also going to be classified under transition metal. In our syllabus, we just need to learn about, okay, this titanium all the way to copper. Yeah, and we need to define. Okay, we need to define what is going to be a transition element. Definition is already given, and that's why I have highlighted over here. This is from your syllabus. Okay, next part, okay, is to look at the shape of the orbitals. Okay, because do remember, if you look at D, normally we write it down as having 5 different orbital. Yeah, so this one we call it as D subshell. Okay, D subshell have, okay, 5 orbitals. Each of them can occupy 2 electrons. And last time, okay, we have learned about P. Okay, P subshell will have 3 orbitals. Okay, and each orbital, okay, they are going to have 2 electrons each. That's why maybe some of you are very aware about this. Okay, px, py, and pz. Okay, so this one, okay, each px and py, pz, they will have their own shape. Okay, the shape is going to be a dumbbell shape, something like this. Screen again, okay, it's not seen. Okay, hold on. Okay, I will share the screen again. Okay, we know that, okay, if you look at the p orbital, yeah, p orbital, normally they are going to have this dumbbell shape, okay, something like this. Okay, so now we need to know, okay, what is going to be the shape of this. Okay, we have 5. Okay, we do not need to know everything. Yeah, but if you look at the diagram, okay, given in your textbook, there are 5. Yeah, there are 5. The one that is required for you in your syllabus is the one that I circled over here, which is going to be 3dxy and 3dz square. Yeah, so let's say you still couldn't visualize why things are getting more complicated and so on. Okay, if you want to visualize it better, okay, you can actually, this is not my video, okay, it's a good animation video to show you about the orbital shape and so on. You can watch that whenever you are free. Okay, but, okay, if I put it in a simple way, if I want to just show you in a very fast way, okay, it's quite easy to understand. I'll just show you. Okay, normally when we draw graph, okay, we will draw graph, normally it's going to be y, and then we put x. Okay, this is our common way of drawing. And we know that there is going to be another axis, which is going to be the z is going to come towards us. Okay, so what we will do, rather than focusing on that z over here, okay, we know that there is going to be another axis, which is going to be z. Now, if I put a different combination of graphs, okay, let's say according to the axis, yeah, I will actually draw, like, for example, like this. Okay, instead of having, let's say, y, okay, maybe I put z over here. Okay, I can also have another combination, which is going to be, I put z over here, maybe x I put over here. Okay, so I hope you can understand this. Okay, there are 3 different combinations that you can have. Okay, and what I will do, I will copy this. Okay, I will copy this. Okay, hold on. I will copy this again. Okay, I will paste it again over here. Now, why I did that? Because there is going to be another different possibilities of things are happening. Yeah. Now, I will show you one by one. Okay. So in this case, okay, I will show you here. Okay. This one, maybe just to make it easier, I will change this into y and z. I'll just put z over here, y over here. Still the same. Okay, doesn't matter. Now, if I draw, okay, if I draw the orbitals, it's not like just like a dumbbell shape that you learn for p orbital. They will have like something like this kind of shape. okay, like something like flower. Yeah, they will have this kind of shape. Okay, so I'll erase this. Okay, how it can be represented, you see, yeah, like your maths. Okay, we normally actually draw somewhere a line over here, right? So we draw something like this. Okay, this is going to be in between. This is going to be one way of arrangement. Okay, another way of arrangement, yeah, same. You just do the same thing over here. Okay, and then okay, over here. It's all not required, yeah, but I'll show you so that you can understand better. Yeah, this is how you write. Okay, how do you write? And then, okay, of course, we need to name them. Yeah, when you name them, there are 3 axes over here. You name them according to alphabetical order. Yeah, so X, Y, and Z. Okay, you follow the alphabetical order. Now, in this first graph, okay, how do I name them? This is going to be the graph, okay, which is going to be, we call it D, okay, X and Y. Okay, so you just follow alphabetical order D, X, Y. Okay, this is going to be the first graph. Now, the second graph, okay, this one by now you should know already, okay, Z and Y, okay, so you follow alphabetical order, yeah. So this is going to be D, okay, Y comes first, followed by Z, okay. And then the last one over here is going to be D also, yeah. So X and Z, yeah, so follow alphabetical order, X and Z, okay, quite simple, okay. Now, is there any other different arrangement? Yes. Okay, you can see. Okay, just now I draw somewhere. Okay, in the middle here. Okay, how about if you have situation where they are going to arrange along the axis? This is going to be different arrangement as well. Okay, along the axis. So I draw all these are going to be along the axis, and they will have their own name. Yeah, they will have their own name. Okay, when you put this, okay, the way we write is going to be now, okay, is going to be known as D. Yeah, but still follow, still follow the alphabetical order. Okay, but we are going to say X, X to the power of 2. Don't ask me why. This is how it is actually written. Yeah, X to the power of 2, and then they put minus over there, and then followed by Y to the power of 2. When we write this, whenever they are going to arrange according to the axis. Yeah, so here, using the same method of writing, you see D, yeah, and you have Y and Z, so it's supposed to be Y square and then Z square. Okay, and then here, this is going to be D, X and Z, so you just put X square to Z square. Now, if you have this situation, it will look like as though we have 6 different orbitals, and we learn they have only 5 orbitals, because maximum number of electrons that D orbital can occupy is going to be maximum of 10 only. Yeah, so something else is happening over here. Happening, basically these two will combine. These two will combine because the reason, you see, if I highlight this is going to be Z. You can see this is Z. And then if you look at this part, this is going to be your Y axis. X axis, yeah, X axis. So if let's say if I put another one more axis over here, which is going to be Y, yeah. If I put Y, you can see according to this diagram, along the axis, there is Y. So if I draw another one over here, it will look like, this is a combination, yeah. So how it will look like, it will look like this. Z, and then there is going to be, it can be X, it can be Y, doesn't matter. When you combine, it will look something like this. Just to make it easier to see, yeah, I'll just put like this, and then there is Y, so there is going to be something like this. So how it looks like, it's going to be maybe difficult to see, but if I draw it in better way, it looks like this, and then, there is going to be something like a flower, like this, and like this, In simple terms, it means that in the middle, it looks like something like this. And these electrons, they can move around. Okay, so it will form like something like a donut. Okay, they will form something like donut. So it means that, okay, these two orbitals, okay, you can combine and then draw them like this. Okay, okay, this is going to be Z, and then this one can be either X or Y, doesn't matter. Yeah, but this is going to be the combined, yeah, combined version. If you combine this, okay, this is what we call as dz to the power of 2. Special, yeah, special. So the one that is required for your syllabus that you're supposed to draw is the donut version, yeah, the donut version, okay, and then xy. Okay, now in summary, yeah, in summary, this is too complicated, Mr. Gopi. It's okay. The one that is required by your syllabus is going to be these two only. So let's actually stick to that. Okay, so let's actually go to checkpoint number 1. If they ask you to draw, okay, 3D XY, how do you draw? Quite simple. Okay, like your maths, okay, you draw the axis. Okay, this is Y. Okay, you draw another axis. This is going to be X. Okay, and then XY, like normal only. Yeah, so you just draw like this, like this, like this, like this. Done. Okay, no problem. Okay, there is no hassle. Okay, make sure you show that, yeah, in this way. Okay, and then if you want to draw this one, it's a special form. Yeah, so no need to worry. Okay, as long that you see Z to the power of 2, make sure, okay, the axis over here is going to be Z. That is very important. Here doesn't matter whether it's going to be X or Y. Okay, doesn't matter. Okay, doesn't matter. You can draw X or Y, doesn't matter, because the other one will be the Y. Okay, so the moment you draw like this. Okay, this is according to the axis. Okay, that is going to be the character for Z. Yeah, and then draw a donut. Okay, draw a donut over here. Okay, so this is going to tell us, okay, this is going to be dz square orbital. Yeah, so do remember each of these orbital can occupy maximum 2 electrons. Okay, that is important also. Okay, so in summary, this one is done. Yeah, so if you want to learn more about this, okay, this one is taken from your textbook. Yeah, they didn't explain about it. Okay, but I already explained how you get it. If you want to visualize more, yeah, please actually go through this video. It's a short video, 3 minutes video. You can actually get a better idea. Okay, if you're still not sure about this, please go through my video again on this. Okay, you will get a better idea on how we end up getting this. But let's say you don't understand a single thing and you want things to be simpler. Yeah, this one is enough already according to our syllabus. Yeah, so I will move on. Okay, now let's actually look at properties of transition metal. We know what is transition metal. Transition metal is going to be a D block element, okay, which can form one or more stable ions with incomplete D subshell. Yeah, so that is going to be our definition. Okay, but what is the property of transition metal? The first property is going to be they will have variable oxidation state. For example, if you look at iron, okay, very common, yeah, iron. Okay, iron, by now you should know that iron, we have iron 2 and iron 3, Fe2 plus, Fe3 plus. This difference in oxidation state, okay, is going to be already telling us the property of transition metal. Okay, they can have multiple oxidation state, but not all of them. Yeah, you can see nickel can have only one. Okay, but that doesn't mean that they are not transition metal. Yeah, as long as, okay, they satisfy the definition, is okay. But most of them, okay, they are going to have multiple oxidation state. If you ask me why, the reason is quite simple. Okay, the reason is going to be, you can look at the syllabus. Yeah, you can see that it is based on the similarity in energy of 3D and 4s. Yeah, why is that? Okay, if you still don't understand, okay, basically I'll just take as manganese as an example. Yeah, if I look at manganese, okay, if you look at manganese, okay, over here. Okay, this is going to be position number what? 1, 2, 3, 4, 5. Yeah, 3D5. So if I write down just manganese alone, okay, it's supposed to be AR 4S2, okay, 3D5. Okay, this is going to be their electronic configuration. So it means that I can remove the electron from manganese, yeah, one by one. Technically supposed to be one by one, okay, but the common one, okay, because not all of them are stable. You see, +2 is stable. So if +2, you remove the 2 electrons from where? You always remove from the 4s first, yeah. You remove 2, so you are going to get 4s0 3d5, okay. And okay, after that, okay, can you remove electron some more? In normal situation, we don't. Why? Because you are starting to remove the electrons from the inner shells. Okay, the nucleus is going to hold the electron very tightly, and then there is going to be difficult to remove the electrons. Okay, your ionization energy is going to be greater. Okay, but it is going to be different when it comes to transition metals. Why? Both of them, they have similar energy level. Okay, that's why, okay, you should know why 4s is fill up first compared to 3d. Yeah, they have similar energy level. It means that electrons can still be removed from 3d. So you can still, if it is 4, you remove 2 and you remove another 2, okay, from 3d, still possible. You can also remove 6. You remove 2 from S, okay, you remove 4, okay, from 3d, okay, but maximum to 7 only. Yeah, why cannot +8? Why cannot +9? Okay, the reason is you remove 2 and then you can remove maximum of 5. That is going to be total 7. If you want to remove the 8 electron, you are going to remove from here, which is going to be in the inner shell. Okay, which is going to be the energy level is going to be more higher, and you are not able to remove the electrons. That is going to be the reason why you have different oxidation states over there. Okay, so you can actually take note like copper plus, and then you have copper 2 plus. Okay, the reason is still the same. The idea is you always remove the electron from 4s before removing from 3d. I'll show you for copper. Yeah, copper is going to be, if you look at your periodic table over here, copper is here 9. Yeah, but copper is special. Yeah, I hope you remember about copper. Okay, copper, when I write down for copper, is going to be AR, okay, 4s2, then 3d 3d here is going to be 3d9. Okay, but this is not the actual way of writing for copper. Yeah, you have already learned this in electronic configuration, because this electron must come over here to form a more stable compound, which is going to be 4s1 3d10. So we don't use this anymore. Yeah, please remember that. Okay, this one you have already learned. Okay, now if I want to have copper plus, okay, you are removing 1 electron. So you remove 1 electron from 4s. So you will have argon, okay, and then 4s0 3d10. Okay, if you want to remove another 1 more electron, which is copper 2 plus, why? Because this and this similar energy level is possible. You remove another one, 4s0, another one. From here, you get 3d9. This is going to be how you're supposed to write for copper. Okay, so this one, okay, please have a look. Okay, the reason why we have variation in oxidation state is because the similarity in the energy level when it comes to 3d and 4s subshell. Yeah, now I will move on. Okay, what are the other properties of transition metals? Yeah, apart from having, okay, difference of variable oxidation state, okay, they will also behave as catalysts. Example, okay, in your Haber process, you have iron catalyst. Iron is going to be transition element. Yeah, iron catalyst. And sometime last time we have learned about homogeneous catalyst. Yeah, homogeneous catalyst is going to be the same phase, okay, as the reactant mixture. And then one of the property for homogeneous catalyst, I think, able to form different oxidation number. Yeah. So in this case, you can see, okay, the oxidation state is going to be different. So they are perfect candidate to become catalysts. Yeah. And then they can form complex ion. Okay. We will discuss more about complex ion. Because of the presence of complex ion, yeah, you are going to have the complex ion is the one that will give you colored compound. Because last time, okay, you would have learned, okay, Fe2 plus. Okay, it's going to be what is the color of Fe2 plus? Okay, you thought it's going to be green. Yeah, what is going to be the color of Fe3 plus? Brown or something like that. Okay, but in reality, they are going to be that color because they are going to form a complex ion. Okay, with what? With water actually. Yeah, so the reason why they are colored, yeah, because they can form complex ion. Yeah, and then we will discuss more on that. Okay, but you see the part that I have actually highlighted over here, okay, from 1 to 4, okay, because they have mentioned that in your syllabus. Okay, but in your textbook, they have given some other properties that you need to know also, yeah, which is going to when we look into transition metal or transition elements. Okay, transition metal, transition elements, you know, now they are metal. Yeah, so if they are metal, of course, they are going to have high melting points. Okay, they are going to have high density. They are going to be hard and rigid. Okay, makes it suitable for construction. Yeah, and because they are metal, they are very good conductors of electricity and heat. Okay, iron can conduct electricity very well. Yeah, copper can conduct electricity very well. Yeah, you should know all this. But the only thing over here that I want to explain more is going to be, okay, first ionization energy. Yeah, so for first ionization energy, okay, I will answer the chat in a while. For the first ionization energy, generally, if you go across the periodic table, okay, we have learned that the atomic radius will become smaller and smaller. Why? Because proton number increases, okay, the number of shell is remaining constant. So the proton, okay, they are going to have, okay, the nucleus will attract the electrons. They will become closer and closer. That makes the atomic radius, ionic radius, all to become smaller. And if I want to remove the electrons, it's going to be difficult to be removed, okay, as you go across the periodic table. Okay, why? Because the nucleus is holding the electron closer to itself. So we expect the ionization energy to increase across the periodic table. But when it comes to transition metal, this part of transition metal, the increase is not going to be significant. So you can actually say, okay, here, there is going to be, they do not vary. This is very important when it comes to transition metal. We expect, okay, it's supposed to be you as the nucleus, okay, having more proton. We expect, okay, the ionization energy is going to be increased. Atomic radius supposed to decrease. We expect ionic radius is going to be decreased, but they appear almost the same. Yeah, so that is going to be another special property when it comes to these transition elements. Okay, now I'll take time to answer the question from William. So for magnesium, okay, not magnesium, yeah. So hold on. For magnesium, if it is +7, will it be still a transition metal, though they won't have any electrons in the D shell orbital? Okay, it's first of all, it's not magnesium. I think you mean Mn, yeah, you mean Mn. Now, if it is 7, okay, they are going to actually have 3D0. But according to the definition, it must form one or more stable ion. Yeah. So Mn, okay, if you look at this, okay, for Mn, even this one, okay, they do not have incomplete. Okay, if it is, they don't have incomplete, but they have incomplete here. They have incomplete over here. As long that they can form one or more incomplete ion, okay, they are considered to be transition element. So it must not be, oh, this one of it formed incomplete. Can we consider Mn as transition metal? The answer is yes, as long one or more, okay, is going to form incomplete D subshell. Yeah. So there is another one more question. Okay, is it right if I don't turn? Okay, okay, Ken. Yeah. Now, if you put, I hope, William, it answers your question, yeah. So as long one of them, yeah. The reason why I said scandium and zinc, 2 plus, scandium 3 plus, scandium, they are not considered to become a transition metal because scandium can only form 3 plus. There is no other oxidation state. Zinc, they can only form zinc 2 plus. There is no other oxidation state. Therefore, these two ions, they do not have incomplete D subshell. Therefore, we do not consider them to become a transition metal. But the other elements, they do have multiple. So this is going to be explaining to your question. Yeah. Now let's actually move on. Yeah. So just now I said about the four main important thing here. The four main important thing is variable oxidation state. They can behave as a catalyst, complex ion. This one, complex and colored compound, is actually the same. Yeah. Because of they are going to form complex, they are going to give you a color compound. That color compound is complex ion. Yeah. So if you look over here, if you look at formation, ligands and complex formation, if you look at the central atom over here or the central element over here, you are going to have Fe2 plus, Fe2 plus. Why I say Fe2 plus, not Fe? Because the charge is 2 plus, and we know it is surrounded by 6 molecules of water. Water is going to be neutral. Yeah. So if all of them are going to be 0, 0, 0, 0, of course, if the entire thing is plus 2, it means that plus 2 belongs to Fe. So that belongs to Fe. Let me share the screen again. I think I think my screen stopped for a while. Let me share the screen again. Now, I was mentioning about the charges, why Fe is plus 2, because the water, the charges is always 0. So if you are surrounded by 6 molecules of water and then suddenly the overall charge is plus 2, it means that plus 2 is coming from Fe. So that's why the central atom, the central element is going to be Fe2 plus, and they will form 6 dative or coordinate bonds. What are coordinate bonds? They are going to give the lone pair of electrons directly to Fe. What is the special property of these transition elements? They have, the moment that they have 4s, 3d, you see 4s, after 4s, they have 4s, 4p, 4d, 4f, they have so many empty orbitals, they have so many subshells, that this subshell, they are capable, to give you the orbital. I think I'm lagging a bit, but again, I will repeat again, the orbitals, they are capable, for the Fe, they have orbitals that are capable to accept the lone pair. So therefore, they can form dative bonding, with the other molecules. And these water molecules, that will give you the lone pair of electrons, they are known as ligands. That is going to be ligands. The one that is going to give you the lone pair of electron, they are known as ligand. Now, the resulting ion, it means you see this entire thing is going to be known as complex ion, and then they are going to form a particular shape. This one we have already learned. If you have something like this, and then you have one coming over here, and then you have something over here, this is going to form what we call as octahedral, octahedral shape. Why they are called octahedral? Octahedral is going to be 8. Why this one is like 6 arrows? Why suddenly octa 8? So basically, if you put from here to here, if you draw over here, this is one phase. From here to here, another phase. Okay, from here to here, behind one more. Okay, you have one more here. So total four faces at the top. Okay, the same thing, four faces at the bottom. Yeah, so 4 plus 4. Okay, looks like a pyramid stack, top and bottom. So it's going to be 8. That's why they're called octahedral. Yeah, but the number of bonds that they form, okay, the coordinate bonding is going to be only 6. Okay, you can actually count. Yeah, so this is 6. Okay, so if you move on further, yeah, you can have different transition elements. Okay, they will form differently based on the size. Okay, because sometimes, okay, cyanide ion, yeah, cyanide ion is actually quite large. Okay, so they will rearrange themselves. Okay, so that they give you better shape. Yeah. So for nickel, okay, nickel 2 plus. Okay, do remember I'm mentioning nickel 2 plus. Why not nickel 2 minus S in the picture? The reason is similar like what I have explained to you just now. Okay, nickel, okay, this one cannot be 2 minus because cyanide ion is going to be -1, -1, -1, -1, -1. Okay, so if the nickel plus 2, then you add with 4 -1, okay, you are going to get +2 minus 4 equals to -2, which is this one. So this must be +2. Yeah, I hope you understand this. Okay, so the central, okay, the central element, okay, the central ion is going to be +2, not -2. Yeah. So anyway, you can see nickel 2 plus because the cyanide ions, they are considered to be large, very big. They will form, okay, 4 dative bonds. Okay, they will form 4 dative bonds with cyanide ions according to the picture over there. The cyanide ions are called ligands, and the resulting ion is called complex ion. The shape, okay, this one you already learned last time. This is going to be square planar. Yeah, this one, all these under shape of molecules. Okay, you can actually go and read further. Yeah. So if I move on to another example here, you can see this is cobalt. Again, this is not cobalt 2 minus, yeah, because Cl is always -1, -1, -1, -1, -1. So what is going to be this? This is going to be +2 plus -4. They will only give you -2. It means that this must be +2. Yeah. So cobalt is going to be the central ion is going to be cobalt 2 plus. Yeah. So the Cl minus ion are going to be known as ligands. Okay. The resulting ion is called complex ion. And because of the shape of this ion, you can see it's going to be slightly different. You see 4 bonding and then 4 bonding. Why different? That's why I told you it depends on the shape, yeah, of the ligands, the shape of the central element also. Yeah, according to this, okay, cobalt 2 plus, okay, will form this particular shape. The shape is going to be tetrahedral. Yeah, you already learned in detail. Even the bond angle also you should know also. Yeah, so each of them is 90 degrees. Yeah, the bond angle over here is 90 degrees. Okay, what is the bond angle over here? 109.5 degrees. The same like what you have learned earlier before. Yeah. Now, so if you put in summary, yeah, what is the concept that I taught you today? So you can see I mentioned about ligand 3 times. What is ligand? Ligand is a species that contains lone pair. Yeah, they contain lone pair, and then they can form dative bond. Yeah, to the central metal ion. So it means that they must have lone pair, and then they can form dative bond. That is going to be ligand. What is complex? Okay, complex is going to be you have that metal or ion, okay, surrounded by ligands. Okay, that is going to be complex. Okay, and there is another new term that I want you to learn, which is going to be known as coordination number. Now, what is coordination number? Coordination number is going to be the number of coordinate bonds or the number of dative bond to the central metal ion. So if you look at here, okay, how this is the central metal, yeah. So how many bonds that they form? Okay, total you can see they form 6. So what is the coordination number? 6. Okay, what is the coordination number over here? Total they form 4. Coordination number is 4. Okay, what is the coordination number over here? Total they have 4. Okay, it means 4. Yeah, so as long we just count at the total number of coordinate bond that is being formed to the central metal or the central ion. Yeah, so I have covered all this. You can read all this, okay? But basically, I'm trying to actually teach based on the syllabus, yeah? So you can actually have a look at that as well, okay? But, okay, if I want to actually look at type of ligands, yeah? We have learned what is ligand. Ligand is going to be, okay, a species, yeah, that contains lone pair of electrons that can form dative bond, yeah? Very important. They must have lone pair. Okay, so example, you see, we have three types of ligand. Yeah, the one that I've introduced to you in this picture, you can see this is going to be water ligand. Okay, they have, okay, lone pair. They can form the dative bonding. Okay, yeah, hold on, Frederick. Okay, they will form the dative bonding, and then, okay, each of one ligand, okay, each of one ligand, they can actually form only one coordinate bond. So you see from here, only one, okay, each of them. Example is going to be water, okay, ammonia, okay, Cl minus and Cn. If you look at some of the examples that I give you over here, all these are monodentate. You can see here, this is only one ligand, one bond, yeah. And then if you look over here, one ligand, one bond, okay, one ligand, one bond. Okay, you can see Cl, Cl minus, Cn minus, and water. They are all called monodentate. Okay, monodentate. And then there is one more, ammonia. Okay, there is no picture. Okay, but there are total 4, okay, different types of ligands that are considered to be monodentate because they form one coordinate bond. Yeah, but sometimes we do have, okay, bidentate as well, because each of these ligand, each, yeah, when I mean each ligand means one molecule, okay, of that ligand can form 2 coordinate bonds, yeah. Example is going to be 1,2-diaminoethane. Too difficult, okay, this is going to be the structure, yeah. But normally they simplify and write it in En. They are inside your syllabus. Therefore, you can use En when you draw also, yeah. So there is another one which is going to be ethane diovate ion, yeah. So both of them, the diagrams are here, and I will show you here. This is considered to be one entire molecule, and you can see this one entire molecule. Okay, at the end of the nitrogen, there is going to be lone pair, and they will form one and another one. So you can see the ligand over here is able to form 2 dative bond or 2 coordinate bonds. Therefore, this ligand is called as bidentate. If you memorize this, good. Okay, if you don't memorize, if you just put En and you put the arrow like this, also can. Okay, it is acceptable. Okay, En. Yeah, and another type is going to be this one, ethane diovate ion. Okay, they have actually simplified. So you can see here, this is going to be the central, and you can see this is going to be the molecule itself. Okay, and then you can see it is joining or giving the forming the coordinate bonding. Okay, so each one molecule is forming 2. Okay, so you can see each one, there are total 3 ligands here. Okay, each of them, they form 2. Okay, they form 2. Okay, but now if I just want to ask you a simple question over here, okay, Poivan, can you tell me, okay, what is the coordination number of this molecule? Coordination number.
Is it 3?
No, yeah, this one, that's why a lot, it's common that students make this mistake. Okay, so let's actually look at the definition of coordination number again. The definition of coordination number is going to be the number of coordinate bonds to the central metal ion. They didn't specify, must come from only from one ligand or how many ligand, doesn't matter. So if you look over here, this is the central, okay, this is the central. And how many coordinate bond? 1, 2, 3, 4, 5, 6. Therefore, the coordination number is still going to be 6. Yeah, I hope you can understand this. Okay, very common where students make this mistake. Yeah, there is another one which is going to be known as polydentate. Yeah, if you have bidentate, it means the ligand can form 2 dative bond. Polydentate means they will form more than 2. Yeah, example in our syllabus is known as EDTA4 minus. Okay, this is going to be EDTA4 minus. Yeah, you can see it's quite complicated. Yeah, but you just need to know that. Okay, there are going to be a lot of lone pair over here. The one that is going to be involved, okay, the ends that will involve in the dative bonding is going to be this end. Okay, I'll just put this end, yeah, and this end, and this end, and this end. Their total, each this one EDTA molecule, yeah, can form 6 dative bond, okay, to this one particular element. So if you look at this over here, there is how many ligand? There is only one ligand. Okay, there's only one ligand, but they form how many coordinate bond? They form total of 6 coordinate bond. Yeah. So it means that each, okay, this one EDTA can form 6 coordination number directly. And because of this, okay, they are known as polydentate. Do you need to know how to draw? I don't think so. Yeah, I don't think so. You need to know how to draw. But do you need to know how to identify or how many coordinate bond? Yes, you must know. Yeah, you must know. The moment you see, yeah, you should know that, okay, how many coordination number and so on. Okay, so now, okay, let's actually, just now Frederick was asking me, can you show us the complex again? It's okay. Now it's the same thing. I put it over here. Okay, so you can also see from here. So you can see the geometry of transition complex. Okay, geometry of transition complex. Okay, if you look at silver, you can see ammonia is going to be a monodentate. Yeah, so you can see 2 bonding pair. Okay, something like what you have learned before. Okay, if you look at coordination number in the central atom, how many dative bond? There are total 2 dative bond. Therefore, automatically, this is going to be, the shape is linear, bond angle is 180. Yeah. So if you look at this example, yeah, nickel 2+, yeah. So with the CN, you can see the coordination number is 4. Okay. Why? Because surrounding the nickel, there are 4 dative bonds. Okay, so what is the shape? Okay, it's known as square planar. Bond angle is 90. Yeah, so if you move on, okay, this is going to be 4. Okay, tetrahedral 109.5. How do we know whether it's going to be square planar or tetrahedral? You just memorize, because there is no way to find out how to identify. But by experience, you will know that nickel, yeah, nickel and CN is big. Okay, therefore they prefer, okay, to form a square planar. If you have cobalt and then Cl, they prefer to form, okay, the tetrahedral. So this one in your syllabus, memorize. Yeah, that's why in this particular chapter you need to memorize. Yeah, so if you move on further, yeah, I have given you something similar over here. Coordination number, you can see this one is going to be, okay, the En. I hope you remember the En. Okay, the bidentate ligand, yes, but you can see the coordination number, it's still going to be 6. Okay, 3 ligands, but 6 coordination number. When you look at the coordination number, you can actually determine what is going to be the shape. Still, it's going to be octahedral, yeah, 90 degrees. Okay, you must know how to draw also, yeah. So that's why it's there. You can actually check. Okay, this one is also common, yeah. The coordination number is 6. Okay, and what is the shape? Okay, the shape is going to be octahedral and 90. Yeah, so similar stuff being repeated again and again. Yeah, the last part that I want to teach you is going to be related to color of complexes. Yeah, because they form complex. Okay, part of the visible spectrum. Okay, if you have normal light, yeah, it is absorbed by the transition metal complex. Okay, how it, okay, in the transition metal, okay, they are known as degenerate. Degenerate means they have same energy level. It means all the 5 orbitals, they have same energy level. That is the meaning of degenerate. Okay, but okay, the coordinate bonding, okay, with the ligands, okay, they will cause, okay, the orbitals over here to split into 2 sets. Okay, and they because they split, they are going to actually form non-degenerate orbitals. If degenerate orbitals means same energy, non-degenerate orbitals are going to be different energy. I think it's understandable. Yeah. Why we have color over here? Because, okay, from having one energy level, they are going to have 2 different energy level. So they are going to be known as non-degenerate orbitals. Okay. So if you look over here, okay, I have actually put it very big over here. Okay, this is according to your syllabus. You need to know how to use the term degenerate and non-degenerate orbitals. Degenerate means same energy. Non-degenerate is going to be different energy. Yeah, and then you need to know this is newly added in your syllabus, not even available in your textbook. So please take note of this. Yeah, so it's quite easy to miss out this. Yeah, later I'll go through this as well. But whatever that it's explained over there, okay, I have put it in a bigger form over here. The coordinate bonding with the ligands, okay, causes the orbitals, okay, the d orbitals, to split into two sets of non-degenerate orbitals. Okay, that is the essence of it. Yeah. So because of the coordinate bonding, okay. Now we have, okay, octahedral shape. Yeah, octahedral shape. So what happened? This is going to be degenerate orbitals. Okay, all of them same energy level. So what happens? Okay, because they form, okay, bonding with the ligands, what happened? They are going to separate into two non-degenerate orbitals. Okay, so what happens? This is going to be splitting. Yeah, and then when you have light, okay, they will absorb the energy. So what happened? The electron over here, they will go over here. They become excited. They will go over there. Okay, when they get excited, that is the time that they will absorb the energy from the light, and they will give you a complementary color, which we can see, okay, as maybe this color, maybe this color, maybe this color. Yeah, so you need to know how to use that. Okay, but in your new syllabus, okay, the splitting, this is shown in your textbook only. Yeah, but do remember, I put it's only for octahedral. In your syllabus, they want for octahedral, they want for tetrahedral. Yeah. Okay. In simple form, okay, if you want to actually read this, go and read yourself. Yeah. But in simple form, okay, it means that in under octahedral, okay, if you have octahedral, okay, you are going to have these two orbitals, okay, which is going to be 3dxy, 3dz2, the one that I told you that you must learn how to draw. Okay, this one, okay, they will experience greater repulsion. Okay, that's why I put over here. They will experience greater repulsion from the other orbitals. So therefore, they will push them. Whenever there is a splitting of orbitals, they will push them to higher energy levels. So they will go up. Yeah, they will go up. And then the concept to absorb the energy and so on is still the same. Okay, but when it comes to tetrahedral complexes, yeah, there is going to be less repulsion, okay, to the two orbitals. What will happen? The two orbitals, they will be still splitting into non-degenerate orbitals, but they are going to split to lower energy level. That is the difference. Yeah, this diagram is not found in your textbook. Okay, they have included in the new syllabus. It's common. Okay, no questions. Okay, from here yet. Okay, but you need to know. Yeah, you need to know. Yeah, very, very important. So you can read over here the color of complexes happen. Okay, because different ligand cause the d orbitals to split by different amount of energy. Okay, because different ligands, okay, if you have ammonia, okay, different splitting, okay. If you have Cl minus, it's going to be different splitting. If you have water, different splitting, okay, with different amount of energy is going to be absorbed. Different color is going to be absorbed from the visible light, and you will see complementary color. That is why, okay, in complex ion, you are going to have different color. Yeah, that's why copper 2 plus, it's seen as blue, but copper 2 plus is actually existing in this form. Yeah, that's why now you should know. Okay, let's say for example, Fe2 plus, they exist in complex form. Yeah, so this one, okay, you can actually go through yourself. Okay, basically they ask, okay, the scandium 3 plus and zinc 2 plus, they are colorless. Why? Okay, they are colorless, okay, because, okay, they are non-transition elements, but you cannot simply give answer they are non-transition elements. Okay, yeah, you just need to write down the electronic configuration. Okay, and then they say if there is a d-splitting happen, yeah. So when there is a splitting, okay, you are going to have the splitting into two degenerate orbitals, right? So there is no electron from the lower energy level, okay, that can actually be promoted to the top energy level to give you the different absorption. Yeah, so that's the reason why it's colorless. You can see for the zinc 2 plus also. Yeah, for zinc 2 plus, okay, there is going to be splitting of orbitals will happen, okay, to create a two sets of non-degenerate orbitals. Okay, but okay, the orbitals are complete, they are full, you know, the two will be at the top, okay, and then this one, okay, the 3 is going to be complete. You see 3d10, all of them are going to be complete. So if let's say this particular electron wants to go there, they don't have any space to go there. Okay, it's complete. Yeah, it's complete. That's the reason why, okay, zinc 2 plus don't give you the color. Yeah, so if you want to read more all this, okay, please go and read. Okay, I've explained over there. And that's it from me. Yeah, I prepared a quizzes for you, but I don't have time. I'll pass that quizzes to your teachers. Yeah, so you can actually try that on your own. 6 questions. Yeah. Other than that, yeah, it's done from me. Yeah. This is going to be the last lesson for the term. So I'll see you again. Okay, next term. Okay, see you guys. Okay, bye.
Thank you, sir.
Bye, sir. Thank you, sir.
Yeah, see you. Bye.
Bye-bye, sir.
See you. Bye.
See you next year.
See you.